Jacob, I think we should, Jacob, I think we should delay work to release until I finish, or at least I get further in Actor Critic.
Yeah.
Right.
So not this Wednesday, basically.
Maybe like Friday or something. Or
Next.
or maybe like something at least give them a bit of time after we get through Actor Critic a bit more, because half the homework is Actor Critic. Okay. Alrighty, let's get started. Cool. So today we're gonna continue talking about policy gradients. And we're gonna get to the end of policy gradients and start actor critic algorithm. Right? So where we're at in the class is we're almost done with policy gradients. We're gonna get to the algorithms that you actually use in practice. And then start doing ADP, approximate dynamic programming, which is off policy reinforcement. Okay, so structure of our class today is going to be, we'll start by just recapping policy gradient, natural policy gradient. Then we started doing trust region policy optimization a little bit. We'll go through that in more detail. Then we'll cover PPO, or proximal policy optimization. And then we'll start studying off policy RL if we have time, right? Cool. So we start from the policy gradient, right? So the policy gradient looks something like this. We basically had an estimator that was grad log pi times sum of rewards. So upweight things that have high rewards, downweight things that have low rewards, and you can approximate this with samples, right? And so this is the first, like maybe 2 lectures ago, what we did. And the issue with this is that it's high variance, right? And so we want to deal with high variance. We added things like baseline, causality. All of these were to reduce variance. But then we said, okay, there's another issue beyond reducing variance, and that issue is if you have the Euclidean norm, which so you're doing gradient ascent, which is basically trying to do steepest descent on the Euclidean norm, right? On the on a quadratic constraint. That's going to be very sensitive to the policy parameterization. So if you're really sensitive to the policy parameterization, you change, like you reparameterize your policy, the gradient looks super different, right? And so we wanted to go from something that looks like this, which is gradient descent, to something that is weighted by a G norm rather than just a quadratic Euclidean norm, right? And so what we said is, what should G be? Let's choose G to be something that keeps the function close, right? Rather than the parameters. And so we said, okay, like gradient descent is going to be keep the parameters close in Euclidean space. And instead we want to say, don't let the policy change too much, right? And if you're saying don't let the policy change too much, we show that the second order Taylor approximation of the KL divergence is this thing called the Fish information metric, which is the outer product of the grad log pi's. And then we showed that if you use this second order approximation and do steepest descent, not in the Euclidean norm, but in the KL divergence approximated to second order, you get this thing called the natural gradient, which is basically gradient descent, but weighted by the inverse of the Fisher information matrix, right? And so remember, the Fisher information matrix is not a second order matrix, it's a first order matrix, which is grad log pi times grad log pi transpose, taken in expectation over pi. The important thing is that grad log pi is the dimension of the parameters. Grad log pi transpose is the dimension of the parameters, which means that product is parameters by parameters, right? And so this thing is great because the F inverse basically reweights different parameters, so it's not sensitive to parameterization. But you have to invert a parameter by parameter size matrix, right? And if you have a huge matrix, that's extremely expensive. Okay, any questions about this before we go on? Does this all make sense? So remember, we're doing steepest descent. We just changed the norm in which we do steepest descent from Euclidean to the KL divergence, and the KL divergence approximate in second order is quadratic with the Fish information matrix. And that's going to give us natural gradients, right? And so the issue we're going to deal with is we want to avoid this like horrible inversion thing. Right? It's just like big inversion. That's always bad. And so the point of trust region policy optimization is to kind of deal with some of the issues in natural policy gradient, right? So intuitively, you can think of natural policy gradient as doing steepest descent, but in the KL divergence norm, which means you take a step, but don't let the policy change too much. Okay? And you want to constrain the policy based on the KL divergence. Okay, intuition makes sense? Good. So we said that there's 2 issues. The first is a huge matrix inversion. And the second is that you don't really know what step size you're taking. So if you're doing steepest descent, you're choosing a step size to do ascent on, right? So if you go back to your update, there's this alpha, right? And if you don't choose your alpha carefully, you can actually have the objective get worse. And this happens for supervised learning too, but for reinforcement learning, it's particularly bad because you'll start collecting bad data and then never recover. So you're doing something that's okay. You take too big of a step size, you start collecting bad data. When you start collecting bad data, you'll never recover after, right? And so you'll start getting into these catastrophic loops where you don't recover. So often what you'll do in policy gradient is you'll take like tiny step sizes. So the issue is you take tiny step size, alpha is tiny, and the variance is huge. So your batch size are huge. So you're taking tiny step sizes with huge batch size, which means you need a shit ton of samples. And so that's kind of what makes it so inefficient. Yeah. Okay. So we want to deal with these two issues, matrix inversion and step size. And then the third issue is that we're also only doing a single step of gradient descent. So if you look at like this thing, you take one step, then you have to re-estimate the Fisher information matrix under your current policy. You have to re-estimate the policy gradient under your current policy. So you have to like take samples again, right? And so you can only take one gradient step before you have to take samples again. So that's what makes it expensive, right? And so what we're going to try and do is deal with these issues, this algorithm TRPO. And TRPO has three key ideas. The first is that you don't want to just do one gradient update per data collection step. You want to do more than one, right? And that's going to be, we're going to deal with that with importance sampling. You want to avoid this huge matrix inversion. So you don't want to use NP dot inverse. You want to try and make this something that is more tractable, right? So that's an algorithm called conjugate gradient, which we'll touch on. And the last is we want to be able to find a way to choose the step size more carefully. And so we don't want to have this like policy getting worse and catastrophically like reducing in performance. And we want to choose our step size carefully. And that's going to give us performance like this. All right. So I know I covered a lot of this last time, but we did discussions. So like it's good to recap. Any questions? So we're trying to deal with these three issues. We're trying to deal with, we don't want to invert the matrix. We don't want to step too far. And we want to take more than one gradient step per data collection. Right? And so those are like, if you ever think of TRPO, TRPO is natural policy gradient with those three things fixed, right? And natural policy gradient is policy gradient, but under it's steepest descent under the KL divergence norm, not the Euclidean norm, right? So if you want to think of how they connect to each other, it's policy gradient is steepest descent, natural gradient is steepest descent under KL, and TRPO is natural gradient made practical, right? With these three things. Yeah. Okay. So let's do a quick recap of what these things mean. So the first issue is that we don't want to have to keep collecting samples when we're doing gradients, right? So if you look at the policy gradient, it's always taken with the expectation under P theta tau, which means under a current policy, right? That's expensive. And so the question we asked is, can we be off policy? Does anyone remember how we dealt with it?
Assume that the changes are small enough that you can assume that you're still in the same mode.
Yes, but there's a step before that. So you're still like, you want to evaluate this objective, but you want to do it under a different distribution. So how do we do that? Yeah. By Q tau or Q tau, there's a different distribution. And then what you can do is you can write this as the expectation under Q of P theta by Q times R. So you're reweighting the function by these things which we call importance weights. These are often called importance weights, P by Q, right? And saying that even if I have samples from a different distribution Q, I can evaluate an expectation that is under P, right? And so you can kind of think of it as like reweighting these samples based on how relevant they are to P, right? So you're saying take samples from Q and only count them by how relevant they are to P. Right? And so all we did is multiplied and divided, regroup the terms. And so we just regroup the terms this way, right? And that's all we did. So this was important sampling, right? So important sampling lets us say we're going to evaluate an objective under a different data distribution, right? And so the issue with it is that it often has these numerical challenges that make it hard to use, right? So we can take that objective right there, policy gradient, right? Like, or the gradient objective, and we can evaluate it under some Q, right? So what would it be under some Q? Well, you're gonna have like expectation trajectories coming from Q. You're gonna have P theta tau by Q tau, right? Times grad log pi, whatever. And the issue here is that this thingy has numerical challenges, right? So often it's not a silver bullet. It's like, yes, you can take more gradient steps for data collection, but it comes with these numerical challenges. And we have to deal with that. Okay, so what do I mean by these numerical challenges? Well, we look at what P theta by Q looks like. Does anyone recall what P theta by Q would look like? What is P theta by Q? So remember that, let's say Q is, let's say you had a, let's say a policy, Q of AT given ST, and P theta is you have a policy pi theta AT given ST. And so we're going to execute these in the world, right? And so P theta tau is the likelihood of a trajectory under pi theta, and Q tau is the likelihood of a trajectory under Q as your policy. So what is P theta tau by Q tau going to be? Like, can we write it out? Can we write it out in terms of states and actions? Expanded and cancel out. So walk me through it, Vishwas. What's the numerator going to be?
Like the first P theta of like S naught, yeah. And the next is P, that's one given us.
And then you have like pi theta, and then you continue, right? And then the bottom has what?
Q of S naught.
But Q only defines your policy. So P is going to be the same, right? So you're going to have the same P of S naught. You're going to have the same dynamics, and you're only going to have a different policy, right? So the important thing is, remember, the likelihood of a trajectory is initial state times dynamics times policy times dynamics times policy times dynamics times policy, right? Which means that the only thing that's different between P theta tau and Q tau is one of them is acting according to pi theta, and one of them is acting according to Q for your policy, but not for your dynamics and not for your initial state. Right? Why is that important? Because this cancels, everything else cancels, right? And so what do you end up with? You end up with a product of pi theta AT given ST divided by Q of AT given ST, right? And so what's the issue with this thing? Well, okay, yeah. So even if you, but let's say you like flipped it, so you never had zeros in the denominator, right? So you like, or you never allowed the denominator to go to zero when the numerator didn't. You still have an issue because you have like a bunch of tiny numbers multiplied with each other, which makes this whole thing like either go to zero or go to infinity, depending on what pi theta and Q are. The other issue is that because they're like a bunch of tiny numbers, any small mistake you make in your estimate is going to be a big deal. So it's going to be really high variance because relative to a bunch of tiny numbers, like even a small change is going to be a big deal, right? And so the problem with these kinds of importance weights is that they're often numerically unstable, right? So you're like multiplying a bunch of ratios of probabilities. Whenever you have ratios of probabilities, it like leads to instability, right? Especially when you multiply many of them. So you kind of want to avoid, especially as you go to like hundreds or thousands of steps, that becomes unstable. And so you want to avoid anything that looks like a product of importance weights. But you can't just like randomly take the log, right? So you could take the log, right? So you could do the log, and then you have to do the exp, right? And so then you have like the log gets more stable, but then it shows up in the exp. And so it's a good point. But here you don't have a log naturally, so you have to do log and exp. And so it doesn't remove the instability.
Why is the high rate?
Because it's a tiny number, right? So it's like
If you do it too many times,
So no, it's due to numerical instability, but if you have like a tiny number, like variance is basically how much does a thing vary compared to the range of the number already, right? The number range is tiny, like any change in that number is huge variance for it. And so like basically if I have a random variable which is like some tiny range, like even a small error in it is for its range is huge, right? And so in that sense, it like the variance is high with respect to the value. Okay, so we want to do things that look like importance sampling, but we don't want to have to multiply a bunch of these like pi thetas over time, right? Or these ratios over time. So what we're going to do is we're going to do a little bit of what looks like a hack, right? And then we're going to try and justify it. A lot of reinforcement learning is doing things that look like hacks and then justifying it with pages of math. Okay, so the first thing we're going to do is we're going to go from this trajectory level sampling, right? So trajectory level sampling says, hey, I'm going to sample S naught, A naught, S1, A1 till ST, AT, right? And I'm going to sample them one after the other. But you can, as we discussed in lecture 1, you can also represent the same sampling process, not by like sequentially doing like you're not there's two ways of doing sampling. You can either do sequential sampling or ancestral sampling, which is S naught, A naught, S1, A1, S2, A2, or you can like sample from the stationary distribution. And so the stationary distribution is if you ran your policy for long enough in the environment, like what is the visitation of different states in your environment, right? And so it's like if I ran my policy from here, you can get a histogram of like how much is S naught visited, how much is S1 visited, how much is S2 visited, how much is S3 visited, right? Over all the states. And the continuous version of this is you just have a probability distribution of like, if I ran pi theta in the environment for over infinite horizon, what is the likelihood that I would visit a particular state, right? And so that's your stationary distribution here, right? And so you can rewrite this objective similarly under the stationary distribution type objective, which is saying the return you're going to get is sample the states according to the stationary distribution, sample the actions according to your policy, right? So this is the likelihood that you got to a particular state and action when you ran your policy by theta in the world, right? So it's saying, what is the likelihood that you got to S and A when you ran your policy in the world? And then you can take like a Q value or like the sum of rewards in the infinite horizon from there, right? So basically this objective and this objective are the same. It's just that you've changed the sampling from this sequential sampling, which is step by step by step by step, to like the stationary distribution sampling, which is saying you sample like a histogram of what is the likelihood of getting to a state when you run the policy, right? So you run the policy, get a histogram, and these two objectives are the same, right? So all we're doing is we're rewriting this objective because it's going to make our importance sampling easier. But these two are the same. And so we can keep going. The problem with this is that, okay, to evaluate this objective, the same as this objective, you have to sample from your policy, right? You have to sample from pi theta. And as theta changes, you have to keep resampling from pi theta. And that's what makes it expensive, right? And so what we want to do is we want to be able to sample from something else besides pi theta. And so what we're going to do is we are going to, let's have a different distribution. Let's call it pi theta I, okay? And we're going to say, let's sample from pi theta I rather than sampling from pi theta, okay? So pi theta I is like a different policy. And so our current policy is pi theta. Pi theta I is a different policy. And we'll instantiate it concretely. But we're going to do importance sampling, same as we did before. So if you remember importance sampling, it is expectation Q, P over Q times R, right? We just reweighted R by P over Q. Now we're just going to do the same thing by setting Q equal to pi theta I, okay? So we're just going to say, let's do importance sampling, but like, let's make our Q distribution some pi theta I. Okay? So I'll tell you what pi theta is in a second, but right now just an abstract policy. Let's call it pi theta I. Okay, so we've said we're going to do importance sampling with pi theta I, which means this thing is kind of your Q, this thing is kind of your Q. It's a little bug. And that thing is your P, right? And so it's exactly the same as like expectation Q P over Q times R, right? This is just importance sampling. So all we did is we took policy gradient, we rewrote it in the stationary distribution form. And then we said, hey, we're going to do importance sampling. Importance sampling is just going to sample from Q, which in this case is coming from pi theta I. And then we're going to take this ratio. And then it's the same objective. So far, we've made no approximation, right? We've just done importance sampling. So it's exact. Okay. Now, the problem here is that this thingy, p theta by p theta I has the same issue as the product of all the probabilities, because p theta is like the long-term visitation. So you have to like multiply a bunch of tiny things. And so this thing is again going to be like numerically unstable. So like the problem with this doesn't really solve the issue. It just pushes the issue to a different place, right? So we have this issue with the product of a bunch of likelihoods. Like the p theta themselves are the product of a bunch of likelihoods, which means that this ratio is going to be numerically unstable again, right? And so all we did is we did the thing in the last slide, but we just rewrote it in stationary distribution form. But the issues don't go away. The issues are still like, the issues still show up here, right? Issues are, this is unstable. Okay, so we did importance sampling, but this thing is unstable. And so what we're going to do is we're going to pretend that this thing is what? And we will see if that makes sense in a second. But the reason that is going to help our problems is because now you're like, if you pretend that this thing is 1, this thing is still sampling from pi theta I, right? You're weighting by an importance ratio, but this importance ratio is not the product of a bunch of terms. It's just one term, right? So you're not multiplying a bunch of these numerically unstable things. This is more numerically stable. It's just one ratio. Now you can take multiple gradient steps on this, right? So you can say the process looks like I would sample from pi theta I. I like collect a bunch of data. And then I take this objective. I take a gradient step on it, right? So I take one gradient step. I moved, let's say my parameters were at theta. I moved to theta prime. Then I can recompute this objective without having to retake samples. And so what's interesting about this objective is that because the samples just come from pi theta I, if you change pi theta, the expectation does not change. Like only the thing inside the expectation changes, which means that you can take multiple samples, right? So the important thing here is that the expectation is under pi theta I. But so if I take gradient steps on this with respect to theta, like this ratio will keep changing, but the expectation doesn't change, which means that I can take multiple gradient steps. So the way the process would work is that you, oh no. The way the process works, okay. The way the process works is that you take a bunch of samples from pi theta I, okay? You compute this objective. Let's call this J theta I theta. Okay, so you're going to take a gradient step on this. So theta is going to move to theta prime. And then you don't need to take more samples. You can still use the same samples, but you have to just change the numerator to be the new theta prime, right? So theta is going to go to theta prime. I'm going to take J theta prime, theta I, and then take a gradient again and take another step, right? And so I can take multiple steps. I can go from theta to theta prime to theta prime prime, and so on without collecting more data. And so the important part here is that this expectation is under theta I, not under theta. So if you're changing theta, you don't have to collect more data, right? And that's kind of what you want to take multiple gradient steps. Yeah. It's a great question. That's a great question. So the important thing, the reason you can't just keep on taking gradient steps here, right, is because you made this approximation. You made this approximation that set this thing to 1. Right? And why is it okay to set this thing to 1? Is basically you can think of p theta s as like what is the visitation under theta, and p theta I of s is what is the visitation under theta I, right? And so if the logic is that if theta and theta I are not that different, then p theta and p theta I are also not that different, because in the long term, if they're boundedly different, their long-term visitation is boundedly different. And so if you take too many gradient steps, this approximation of setting it to 1 is very wrong. And so it's often an empirical choice, but you take like 4 to 5 gradient steps, not like 50. Does that make sense?
Like moving from the R down to the S, to the statement utility bound. So in the top one, you were taking expectation over trajectory, right? So you moved it to expectation over sample. So is it like take just an average over all the samples?
Yeah, so this is so Q is kind of like it's like the long-term value of a state and action. So it's saying if I start a state and action and I acted for infinite horizon, right? Like how good do I do, right? And this is saying like what is the states that I visit under my policy? What are the actions that my policy takes? And this is how good are those states and actions in the long term under my policy, right? And so this could be like you can think of this as the long-term goodness of S and A. This is saying which S's and A's do you visit, and you average the long-term goodness over the S's and A's that you visit to get the goodness of your policy. Right? Okay. Okay. Good. So so the important thing here is that we took this approximation, we got rid of the numerical instability, but the approximation only makes sense if p theta and p theta I are close, which means you can take some gradient steps, but you can't take infinite. You take some gradient steps while that approximation is valid, and then you have to take samples again, right? That's it.
When you implement this, it is like you take gradient step and then you use the space lifted by the original. And you just ask the new policy, like, what would you do in these states? That's how you.
That's how you like you take the same states and actually sample a batch. You just recompute the importance space.
Got it.
So the way you typically instantiate this is that you set theta I equal to theta, right? And then you like keep the same theta I, you collect a bunch of data, and then you move theta a bunch of times to something else. And then you set this thing to theta I plus 1. And then you repeat it again, right? And then you like, so it's like theta I is equal to theta, theta moves for a bunch of steps, then you reset theta I plus 1 to the updated theta, take more data again, and then take more steps, right? So earlier what we used to do is we would collect data under some theta, we'd take a step to theta prime, and then we collect more data. Now what we're going to do is we're going to collect some data under theta I. We're going to have theta and theta I match here. They're going to move theta a bunch of times to some, let's call it theta prime prime prime. And now you're going to collect data under theta prime 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 and then do a bunch of steps, right? So now what you've gotten is the ability to do these steps without recollecting data. Yeah? So that's the nice part about it. Yep. So you just set theta I to your current policy, right? So let's say you started some policy, you set theta I to your current policy, collect some data under your current policy, and then you move theta without moving theta I. So it's kind of like you start theta and theta I at the same place, and then you move theta to like somewhere, and then you set after some number of steps, you set that to theta I plus 1, and then you take more steps here. So you always set theta I to your current policy, but you freeze it for some number of steps before recollecting data. Just random. So you like typically what we'll do is we'll set theta I to like theta to start, and theta will just be like the random initialization of a policy, right? So it'll be like you like have a Xavier initialization for your policy or something, and so that's how you start it. That is a good question. In PPO and TRPO, I haven't seen people do that, so I don't know the answer, but I expect that it would be fine. It'd be fine to do an exponential moving average, but I haven't seen anyone do that. It'd be worth looking into. People do it for Q learning, but not for this. Yeah, go ahead, Lynn.
theta ratio flaw because it's the weight, not probability.
No, it is probability. So phi theta is probability, it's a probability distribution, but you're not multiplying many of them. And so like, if you look at like that guy, you're multiplying like P of them, right? So you're like taking 1 ratio, 2 ratio, 3 ratio, multiplying like 500 of them. And over here, this this is like a one-step thing. It's telling me at this state what action would I take. Whereas this thing is like the long-term visitation of states over many, 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 many steps, right? So this ratio is kind of like it's kind of like the product of a lot of probabilities. And this thing is just like one probability, it's like at one step. And so the point here is that when you multiply lots of these time step weights, they blow up. But if it's just one, it doesn't blow up. Yeah. Okay. So so that's our first key idea. They often call your surrogate objective, but you want to do importance sampling, but you want to avoid this like blow up over time steps. And so you're going to make this approximation that removes the stationary distribution. But that's only valid for some number of steps before you have to redo it. Okay. So that's the first idea. Everyone kind of with me? So we did the same thing as policy gradient. We just did the importance sampling version, and we replaced the importance sampling. We like made an approximation. And that let us take multiple steps. So you can go from NPG. We still haven't changed anything else. You just go from NPG, and you just like natural policy gradient, and you just changed your objective to be importance sample. Right? You can still do it with the matrix inversion. You can still do everything else the same. Anytime you have an expectation, just make it this importance sample ratio. Right? Okay. So the next issue we have is this issue of this huge matrix inversion, right? So we have this like F inverse, right? So in natural policy gradient, if you remember, we did like theta is equal to theta I plus alpha times F inverse times the gradient, right? Or I wrote that poorly, sorry. Theta I plus alpha F inverse G, right? So we had an objective like that. That's painful because you have to like get F inverse, you have to multiply F inverse by G, huge matrices. I want to avoid it. How might I be able to avoid inverting a giant matrix with like analytical solvers? Like, is there a different solution we can take to solve to like you don't really care about F or F inverse, you only really care about getting F inverse G. Right? Because the only thing that's going to update your policy is F inverse G, and F inverse is just a means to get F inverse G. So if I want to get F inverse G, what's a different idea that lets us get F inverse G? Yeah. Something else. Yeah, I can't remember. That's possible, but I think we're going to do something simpler than that. Other thoughts? Like we don't want to do analytical inversion. We want to do something that's like more scalable with modern compute and modern optimization methods. And the main point is we want to get F inverse G, but I don't want to sit and invert F. So what is a different idea to get there?
You want to stop this so you generally have access.
Right.
The first one.
Yeah.
Higher.
Exactly. Right. And so what you're going to do is you're going to convert into an iterative minimization problem. So you're going to say you want to solve, like if I can solve fx equal to g, the solution to fx equal to g is f inverse g. Right? That you just multiply both sides by f inverse. So if I could solve fx equal to g, then I can get f inverse g, right? So it's a system of linear equations, right? And so the nice thing about solving fx equal to g, like one way to solve fx equal to g is find f inverse and solve it analytically or the pseudo inverse. But if you look at this objective, right, which is a quadratic objective, if you find the minimum of that quadratic objective, that solution satisfies fx equal to g. And the idea is simple, just take the gradient of this, equate it to 0. And the gradient of this is equal to fx minus g. If you take the gradient with respect to x, right? You equate that to 0, you get fx equal to g, which means that x is equal to f inverse g. Okay. So if you have a quadratic function and you take the minimum with respect to x, the solution will be f inverse g. Yeah. And so now what you've done is you've converted it from something that has to analytically compute the inverse of f to something that just solves a minimization, a quadratic minimization problem. Okay. And so as you were saying, basically what we've done is we've said x is the solution to fx equal to g, and that is the minimum of a higher order optimization problem, which in this case is a quadratic. So if I could solve that thing, then I get the x that gives me f inverse g without ever needing to invert, right? So I just start at some random x, and then I like do some optimization thingy. It gives me x star, and then x star is basically f inverse g, and I use that as my gradient, right? And so the important part is that we just need to instantiate this optimization process, and we need to solve it efficiently. And the solution is going to be f inverse g, which I'll just directly use to update my parameters. So like once I solve this, it'll give me an x. And then I say theta I plus 1 is equal to theta I plus alpha of x star. Right? Because we know that x star is approximately equal to f inverse g. Yep. Questions?
Oh, that is an outer product, right? So can you
Yes.
exploit the fact that it's symmetric and positives and negatives?
Yeah. Yeah, we do. So that's what the conjugate gradient algorithm is going to do. So it's PSD, which is going to make it like easier to solve. Yeah, good point. So essentially what we want to do is we want to solve that problem, and the solution is just going to be our gradient update. So the most obvious way to solve this problem is just gradient descent, right? The problem with gradient descent is always just like the whatever you call this problem, like fluctuating gradient problem. It's like, because it's not geometry aware, gradient descent often like is an inefficient technique to solve these problems. And so what John and Sergey and others kind of suggested in this paper was to use this technique called conjugate gradient. And we're not going to get, conjugate gradient is a really rich and awesome technique. The link down there kind of like is a really nice tutorial on conjugate gradient. I just want to communicate the vibes. And so how many of you know what coordinate ascent is? And so gradient descent is basically you take your level set. You're always going to go perpendicular to your level set, right? You're taking the gradient. And what coordinate ascent does is it like, but like the gradient ascent can move in more than one direction at a time. And so gradient descent kind of changes multiple, like if these are the parameters, you can see that it changes multiple parameters at a time. So it goes in these like zigzag paths. What coordinate ascent does is it tries to go in like one parameter at a time, right? So it kind of like maximizes one parameter, then maximizes another parameter, and maximizes another parameter, and so on, right? And so you can kind of think of like, if this is your optimization problem, gradient descent is doing something like this. Coordinate ascent is doing something like this. Right? So it's like one at a time, one at a time. And coordinate descent doesn't always converge, but conjugate gradient is very related to coordinate descent in that it's trying to like, the problem with gradient descent moving around so much is you need more gradient steps to solve it. What conjugate gradient descent does, or conjugate gradient does, is it tries to find these like orthogonal directions to move in your space. So rather than just like move, like in gradient descent, the next direction doesn't have to be orthogonal to your previous direction. So you might be redoing some of the work you did last time or undoing some of the work you did last time. Whereas what conjugate gradient does is it says, let me take this step and my next step will be orthogonal to the previous step. And the next step will be orthogonal to the previous step, right? And so then the number of steps is approximately like the number of dimensions of your space, whereas in gradient descent, it's much larger. And so the general intuition behind conjugate gradient is that it like keeps taking orthogonal steps in your space right? Rather than taking steps that are just the gradient under your current objective. And the point of doing orthogonal steps is that you reduce the number of steps you need to solve your problem. And this works particularly well for problems that have some sparsity, but like that's reasonable iteration. You can see that you're like undoing some of the stuff you did last time. And so you have to redo it and undo it and redo it. Whereas conjugate gradient looks a lot more like you're going orthogonal to the previous step, right? The important thing about conjugate gradient is that it's not exactly orthogonal, it's F orthogonal, which means that it's not that D transpose D is equal to 0, it's that D transpose F D is equal to 0. So you can kind of think of it as if you have like, you know, like symmetric geometry in your problem, then like this thing and this thing are orthogonal. But like when your problem has a different F, which is like warps, you can think of this as warping your space, then you want to take things that are orthogonal under your warped space. Right? So saying things that are orthogonal under your warped space. And so you can kind of think of it as like F is like stretching your space. It's like an ellipsoid. It's like stretching your ellipse. And you want things that are orthogonal under that stretched ellipse. But the basic point is conjugate gradient is like gradient descent, but taking things that are F orthogonal, right? And gives you like a really efficient method to do them. We don't have to go into the details, but you can just like call scikit-learn conjugate gradient. It'll work. Yeah, that's quadratic. Yeah. In X, it's quadratic. Cool. But the important thing is we solved it completely. We went from this thing where you had to invert F to something where you just do iterative optimization, so you never have to invert anything, right? So you're just like taking these gradient steps and you're like iterating. So you're like converting a huge matrix optimization into a for loop. And this works particularly well when your matrices F are pretty sparse. And then what sparse means for Fisher information matrix is that the parameters don't affect each other that much. And so it's effective when you have neural nets with lots of different layers, when some of the layers don't affect the other layers that much, then this is a good approximation. So the point of conjugate gradient is that we avoided F inverse, we converted into solving this quadratic problem. Right? Quadratic problem solution would be F inverse G. Same solution. We just never need to get F inverse, just get F inverse G. Gradient descent is kind of inefficient to solve that quadratic problem. And so they suggested this thing called conjugate gradient. Conjugate gradient is just taking orthogonal directions in the space to do their search rather than the gradient directions, which may not be orthogonal. That's it. Yeah. In most cases in life, you won't have to like rewrite conjugate gradient. You can just use a library for it, but it's a really cool method. So I'd recommend reading about it.
Question. It might be a tough question.
That's fine.
If conjugate gradient is more efficient, why don't they use the normal neural networks? Is it because it's more efficient when it's a quadratic?
Yeah. So conjugate gradient works for problems of like that nature, not for all problems. Okay. Everyone followed me? So first thing we did is we went from on policy updates where you collect data every time to off policy updates with important sample. The second thing we did is we said we want to avoid huge matrix inversion. So we're going to convert it to this like iterative minimization problem. We're going to solve it with conjugate gradient. You could also solve it with gradient descent. It's just more inefficient. And then the last thing we're going to deal with is the step size problem, right? So one way to think about this is that if you compute your gradient direction, right, which is our whatever F inverse G, the problem with it is that it like may take a step that's too far, right? So like, for instance, maybe you took a step that is too far. Maybe you took a step that actually reduced your value. Maybe this one is not that illustrative. Let's consider a step that is so far that it actually like reduced your value. You really don't want to take that step. So even though your direction is correct, you need to make sure your step size is set properly, right? And so the idea behind this thing called backtracking line search is to just is literally to backtrack. So it's to start from a large value of your step size and then to keep reducing it until it satisfies some sort of threshold, right? And so the idea is that you start with something that's big, right? And maybe it makes your value worse. And then you keep reducing it until it makes your value better, right? So it's like, I should really fix this illustration, but basically you started with something where your value was worse. And then you said, okay, I'm going to make the step size smaller And step size, so like this thing brought us down here. This thing will bring us down here. And at some point you have a stopping criterion and you stop your optimization, right? So you're just saying that you've chosen the direction, you want to choose the step size. You just keep making your step size smaller until it like satisfies your threshold, right? And so in our case, our threshold is going to be, let's say you have some objective, J theta, okay? You're going to do an update on J theta. You've computed a gradient direction. Let's call it F inverse G, okay? So you've said, okay, theta I plus 1 is theta I plus alpha times F inverse G. Okay, so what we do is we set alpha to be big. Set this to be big. And then we'll see that actually J of theta I plus 1 might be less than J of theta I, even though I wanted it to be more. Right? So I'm trying to do ascent. But if I took too big of a step size, I'll have something that reduces the value rather than increases the value. Right? And so what I'm going to do then is I'm going to say, hey, what if I just half the alpha? So what if I set alpha to alpha over 2, right? So then I've like said, okay, now I'm going to take a step, but I'm going to do it with alpha over 2. I'm going to check again, was J theta I plus 1 better or worse than J theta I, right? And so you keep going until you find that J theta I plus 1. And okay, if it wasn't, then I'll half alpha again, right? And so you keep going until J theta I plus 1 is actually better than J theta I, and then you stop, right? And so I think this illustration could be a bit better, but maybe one way to think about it is you start here. You started like pretty bad, right? So you started with something that was too far down. And then you said, okay, let me half the step size. Let's call it here. So the next time you're going to do it, you're going to say, okay, I half my step size and I'm still worse. So I half my step size again, right? So I say, okay, I'm going to half my step size again. And now I was here, half my step size. I find something better. Done. Right? So you just like start from a big thing, half, 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 or like multiply it by some number less than 1 until you get to a number that you're happy with, and then you stop. Okay. So written in typeset form, right? You compute your search direction. So in this case, it's going to be the output of our previous conjugate gradient procedure, the F inverse G. Then you're going to start by setting it to some maximum step size, right? So let's say it's some biggish number. And then you're going to like, you're going to try and compute the value, try and compute your objective when you took that step, right? Under your current step size, let's call your current step size T. And you say, okay, I'm going to take a step under my current step size T in my search direction S. And if it's worse, then I'm going to like set T equal to beta T, where beta is less than 1. Right? And so you want to like reduce your step size, but you want to do it like slowly. Right? So it's like you're going to start with a large step size. If you drop value, you reduce it. If you drop value, you reduce until you have a stopping criterion. Let's say your value has to increase, right? And so once it increases, you stop, you take the step, and then you repeat. Okay, questions? That makes sense. It's like it's no tricks. It's just like choosing step size by like trying a bunch of step sizes until you get something that improves. That's it. Okay, so all the TRPO is really just a combination of these three tricks. Sorry, I'm just gonna. A combination of these three tricks. The first being on policy updates, going to important sample updates, so you can take multiple steps. The second is avoiding F inverse using conjugate gradient. And the third is just doing backtracking line search with your step size until you don't step too far, right? And so we're just saying combine those three things with natural policy gradient and you're done. So I just copy pasted this from John's paper. But essentially, the only three things that are really happening here are those three things. So policy gain to natural policy gain is just to steepest descent under a different norm. Natural policy gain to TRPO is just do importance sampling, don't do matrix inversion, do conjugate gradient, and then do backtracking line search. right? So those are the two things. Three changes. Yeah, so the nice part about the objective that we had is that you don't actually have to rerun the policy, right? If you look at like this J theta, right? It's under the same data. And so you never have to like you never have to recollect the data because it's important sample. Yeah, exactly. Right. So like you can evaluate this objective without having to recollect the data. And so that's what makes it like doable. It's a good question. But if it was like the non-important sample objective, you'd have to run it again.
Yeah.
Okay. So yeah.
Like the conjugate gradient, right? How many steps do you usually take? Because you said it depends on the dimensionality of
Yeah.
if I still have like a million parameter model,
Yeah.
still gonna take a while.
It often depends on how sparse your F matrix is. Like sometimes what happens if your F matrix is pretty sparse, then a few steps can get you there. But if your F matrix is not sparse, then it depends on your parameterization. I don't recall exactly empirically how many steps they took, but it's in the appendix of the paper. But really it depends on the sparsity of your F matrix, which depends on how much are the parameters coupled to each other. Okay, so there's some theory you can write about it, right? So there's like theory of monotonic policy improvement, but the intuitive way to think about it is that the objective you're optimizing is kind of the thing on the right. You can kind of think of the right as it's optimizing this is your important sampled objective. This is your important sampled objective. This is kind of, if you remember natural policy gradient, there was a KL divergence constraint, right? And so you're saying like you want to maximize your important sample objective with the KL divergence constraint. This is like the right-hand side is the objective for TRPO, right? And what they're showing is that if you're optimizing the objective for TRPO, and this is the true performance of your policy, and it's showing that it's like a lower bound. So if you maximize the lower bound, you're like maximizing, you're like improving the performance of your policy pi tilde, right? And so the theory is a bit dense and a little painful to go through, but essentially the intuition here is that this objective on the right is the TRPO objective, and it is a lower bound on the true policy performance. And if you maximize the lower bound, then you maximize. They also show that the lower bound is tight in certain cases. And so if you maximize the lower bound, then you're like maximizing the policy performance. So you're monotonically increasing the policy performance, or at least it's non-decreasing. And so there's some nice theory that they do. We don't have to go through it, but really the main thing to remember is like that objective on the top is the TRPO objective. You maximize that. It's a lower bound on the true policy performance. And so you have this policy improvement. For those of you who are interested, I'm happy to go over it in office hours, but it's a little too involved. Cool. So this is some videos from the olden days. Let's see, does it play? But there was actually a bunch of the simulated characters that were made at UW by some of MO's students. So the swimmer and the walker and the hopper were made at UW. But John kind of got them to like walk around with TRPOs and others. So, these are all Mojoko.
The policy is.
And they all use like tiny neural nets, but since then we've started training PPO with much bigger, or even TRPO with much bigger models. Yeah. Alrighty. So, yes.
Question, why is like backbreaking light search, especially efficient and fast vision? Because
You should just use it everywhere. The problem is what you're saying is like in reinforcement learning, if you don't have the important sample objective, you can't even do backtrack. And so it's like, it is a thing we should have done, but you can't do it if you have to be on policy with your objective. So in like supervised learning, they often do it anyways. Okay. So the issue with TRPO, or one thing we haven't talked about that much, is is the advantage estimate, or by the advantage estimate, I mean basically, if you remember, we did in policy gradient, we did grad log pi times sum of reward, right, minus some baseline. Yeah. And so we talked about how to like, if this is your gradient, we try to make it F inverse G. We made this all efficient. We did all of this stuff. But like this thingy is still pretty high variance, right? So this like sum of rewards minus baseline, which is often what you'll call an advantage, right? Is still pretty high variance. So it's the thing we discussed a couple of classes ago where we wanted to reduce the variance by subtracting this state-dependent baseline, right? That thing is still high variance. And so the other thing that often helps TRPO is to try and make that estimation a little lower variance. Yeah. And so it's the same issue as like dealing with the variance of this by subtracting this. We're saying that this is still too high variance. Can we drop it even further? Yeah. Okay. So, or the other issue will kind of come back to the end, but let's start with advantage estimation being too high variance. So we've done? What we've gone from policy gradient to natural policy gradient to TRPO. And inside policy gradient, we also did like this minus baseline trick, right? We did like sum of rewards minus baseline. And that helped. And so this is kind of what we've covered in policy gradient. We've covered basic policy gradient, we've covered baseline reduction, natural policy gradient, make it practical with TRPO. Right? That's what we've done. And now we're going to go back to the baseline problem and say that's still too high variance. So we're going to try and reduce the variance. Okay. So, so right off the TRPO paper, they had this paper called Generalized Advantage Estimation, which is kind of neat, but it's basically trying to say, let's try and reduce the variance of this estimator. So this estimator is the same thing that I said earlier. It's basically sum of R minus B, right? So this is your value. This thing is your baseline, often called a value function, right? But a baseline is just some state-dependent function, which is kind of like your average rewards, right? And so you're going to take your sum of rewards in a trajectory and then subtract the average rewards from the state S1, right? And so you can think of this as like, how much better was my trajectory than the average? Yeah. And so that's why it's called an advantage. It's like, how much of an advantage do I have over the average? Okay? So you're saying that this is what we did in policy gradient. We took grad log pi and we multiplied it by sum of rewards minus baselines, which is exactly the same as this objective. Right? So if you look at this objective, it's like sum of rewards minus the baseline. Right? B is B, but it's basically the same. Yeah, everyone follow that? No? Maybe? It's just another name for P. Just it's like your average, it's your average sum of rewards from a particular state. So if you remember what we did for the baseline, like what we did for the baseline is we said, okay, you're going to have sum of rewards, you're going to have some state-dependent function, right? And then we said our state-dependent function is just going to be take a bunch of rewards and take their like average from a particular state, and that's going to be your baseline, right? And so that is the same thing as V. It's just often called a value function for historical reasons. But V is B. Let's just write that down. V equal to B. Yep. Okay, so that's what we typically do for advantage estimation. And so what John and some others thought about is, hey, this thing is high variance, but then you can notice that there's like a recursion in this objective. So you can see that like this objective is R1 plus gamma R2 plus gamma squared R3 till gamma n minus 1 Rn minus Vs1. Okay. So I just rewrote it again. Now, if you look at this stuff, it's R1 plus gamma times R2 plus gamma R3 plus gamma squared R4 till gamma n minus 2 Rn minus Vs1, right? All I did was I took gamma out from the second, like from terms 2 to n. I took all of these terms, I took gamma out, right? And so you can see that like all I did is I wrote this thing as this thing by taking gamma out of all of this, the 2 to n terms, right? But the nice part is that you can see a recursion, right? You can see that this thing, let's see, that was sum of rewards from step 1 to n. This is sum of rewards from step 2 to n, right? And as I was just saying, the value function is just the average sum of rewards. So this thingy is kind of like your value function from step S2, right? So you start at state S1, right? And you're saying that like you recursively break down the sum of rewards. So you say R1 plus gamma R2 till gamma n minus 1 Rn minus V of S1. You take all of these terms, right? You take gamma out, R2 plus gamma R3 till gamma n minus 2 Rn. And you notice that this thing is kind of like the value function at the next step. It's just recursion, right? So you're just saying that like, this was like your, the value function is your average sum of rewards. This thing is like your value function from the next step. And so what that allows you to do is rewrite this estimator as this, which is R1 plus gamma times the value function at the next step minus the value function at the current step, right? So value function is just the average sum of rewards. And say, you can kind of think of it as like, how good is my state in action at a particular step is how good is my state in action at the first step, plus how good is the next state that I get to, right? And so you're like saying, another way to rewrite this objective, just using recursion, is to write it as R1 plus gamma V of S2 minus V of S1. Right? So it's like using the fact that you can like take gamma out of like, don't worry about all the stuff in the middle, just look at A1 and AN. So AN is what you call a fully Monte Carlo estimate. So it's like just adding up the rewards at all the steps. And A1 is saying, well, everything after the second step is also a value function, but just at the next step. Right? And so it's saying that another way to estimate this objective, if you had a value function, was to say that the advantage is R1 plus gamma, the next value function, minus the baseline. Right? And so these are just 2 different ways of approximating the same objectives. This is like not that intuitive. So please ask me questions. So it's basically saying, it's like it's saying that a value function is essentially a sum of rewards. And it's saying that it's kind of like, intuitively, you could think of it as the value function from the first step is the first reward plus the value function at the next step. Right? So the value function is the sum of rewards. You're saying it's the first reward plus gamma times the value function at the next step. Yeah.
Wait, so the reason why we subtracted by V of S1
Was for variance reduction.
is to remove the bias that is introduced by the scale.
Scaling, that's right.
Yeah, but what's the point of this?
Okay, yeah, I haven't gotten to the point yet. I've just shown an equivalence. It's a good question. Why do I do any of this, right? So the reason to do any of this is because this thing is a completely single sample estimate, which means that I'm only taking the rewards along my current trajectory. Whereas if V is a learned thing, right, then what V allows me to do is it's like a learned thing which has some generalization, which means that even if there's other trajectories which are like nearby, right, they're all learned. V is learned on all of them, which means that it allows me to share information across states that are nearby. And so you can reduce variance because it's not just a single sample estimate, it's more like a multi-sample estimate, right? So let me see if I have a graphic here. I have a graphic somewhere. One sec. Meh. Oh shit, a lot of slides. Yeah, so here's one way to think about it. The single sample estimate is kind of what's shown on the top, right? So you only take the rewards on your current trajectory. What a value function allows you to do is it allows you to share some information between different states. And so the reason to use an estimator like I was talking about is because while this thing is just a single sample estimate, this thing allows you to share information across trajectories because V is a learned thing. V is not like a analytical thing, right? And so like the point here is that this thing is going to be, we'll go into this in a lot of detail in off policy RL, but the intuition here is that this thing is high variance low bias, right? So it's unbiased. But this thing is low variance, as in if V is estimated correctly, I have a multi-sample estimate because I could share information across lots of stuff. But if V is wrong, then I'm screwed. Right? If V is wrong, then I have like, this thing is completely wrong. Right? So this is like low variance, high bias. Right? So the point here is that you can take this estimator, which is essentially sum of R minus B or V, right? And you can construct different levels of estimation going from a one-step estimate to an n-step estimate, and they trade off between bias and variance. So this thing is low variance, high bias. This thing is high variance, low bias. And so you kind of want to choose an estimator which trades these off optimally. And so one way to think about this is like the way this fits into our whole thing so far is we did policy gradient to national policy gradient to TRPO, but all of them have a sum of R minus B term, right? And in all of them, you can kind of replace the sum of R minus B term by like some mixture of these approximators to better trade off bias and variance. Okay, so we'll go into like this idea of value functions in a lot of detail by the end of this class. But the intuition here is that you can kind of combine things that are like high variance, low bias, and high bias, low variance. You can kind of combine them in a geometric sum to do better than any of the extremes, right? And so in practice, when you use policy gradient algorithms, you don't actually just do sum of R minus B. You do this like weighted sum of many different approximations. And so we won't spend too much time here. But the important thing to look at is if you look at performance or cost, there's the extremes where you like only choose the high bias, and the other extreme where you only choose the high variance, and the optimum is like the stuff in between. And so the important part I want to convey here is that you can have multiple different estimators for the sum of reward. You can have the normal estimator, you can have a fully, this is often called a bootstrapped estimator, but an estimator with recursion. And these have different trade-offs, and you want to kind of combine them to get your thing that you apply in practice. Don't need to get too into the weeds here, just kind of like intuition is enough. And we'll get into the weeds. Okay, so we covered a lot of stuff. Let's kind of make sure we're on track, right? So we did PG to NPG to TRPO. And then we said we're going to reduce this with like, we're going to reduce variance with causality. So we're going to do like return to go, ignore things in the past. And we're going to remove things with baselines, right? And then we briefly discussed this like variance reduction technique with like trading off bias and variance, right? And so that's kind of like a rough roadmap of policy gradient, right? We've like started from the most naive thing, and you've dealt with variance, you've dealt with sensitivity to parameters, you made that thing practical, and then you've like tried to make the estimator even lower variance. Okay, so that all leads up to the algorithm that you'd often use in practice, something called PPO, right? And so the idea behind PPO was like, okay, we had this complicated thing, we like spent like 1.5 lectures on it. Still pretty complicated, right? So can we take the vibes from TRPO and put them into an algorithm that avoids this complicated optimization, right? So we're doing this like optimization with conjugate gradient, and we're doing all of this backtracking, line search, and all of this stuff. Can we make something that looks more like supervised learning? And so the intuition here is that, okay, trust region policy optimization and natural policy gradient are just saying, to steepest ascent while restricting how much the policy changes. What if we just restricted how much the policy changes directly? Right. So we're saying that like the policy change is basically the ratio of phi theta and phi theta I. We are going to not do all of this fancy stuff. We're just going to clip pi theta by pi theta I. Right. So we're just going to say like essentially you can think of pi theta by pi theta I as the ratio of how likely an action was for your new policy versus how likely it was for your old policy, right? And so intuitively, you can kind of think of it this is your old policy. Let's say this was your new policy. At each of these steps, you can take this ratio, right? This ratio is basically pi theta by pi theta I. Right? So you moved your policy distribution, and your ratio changed by some amount. So the whole point of all of this stuff was saying, don't let pi theta change too much from pi theta I. Well, if you just distill the essence of that into a simple algorithm, you do the same thing, but just with clipping, right? So you just say like, you want to still do your same, if you remember important sampled objective, it looked like sample according to pi theta I, do pi theta by pi theta I times like some sum of rewards thingy, right? That's what we did earlier. And then we like, this was our objective. We took the gradient of it. We did this F inverse stuff. All of that is what we did for national policy gradient on TRPO. Instead of doing all of that, just like take this thing and clip it. Okay. And what is it? Why does it matter if it's clipped? It's basically if it's clipped, theta can move some amount to theta I. And then after that, it stops getting gradients, right? So when you like clip something, it stops getting gradients after it goes too far. And so you can like safely take gradient steps on this thing because after some amount, this thing gets totally clipped off.
Is A advantage?
A is advantage, correct. A is basically sum of rewards minus value.
Where does the action come in here? So this is like, it's like Q for one step and then it's the advantage after.
No, so I would say that like what you want, like the reason you want advantage is because it's telling you how much better that action is that you took than the average action. And so it has to be like how much better is your action that you took in that trajectory than the average action.
Sorry, what I mean is before we define advantage just over states, states and actions, what's different?
So you're always going to define advantage over states and actions. So advantage is basically you take, sorry, one sec. You take your sum of rewards, okay, in a trajectory from time step 1 to n. So it's taking this trajectory, and then you're subtracting the value function of your initial state. So this is kind of like telling you how good was this trajectory. This is telling you how good was the average. And this thing is essentially going to be a function of both S and A because it's going to tell you how much better is this action than the average action. Okay. And so even if you look at like, at least it should be, if you look at my notation from earlier, advantage is always function of both S and A. Yeah.
If you're approximating value function, so if your value function is ideal, so your advantage will be.
So value function is the average. So value function is saying what is the sorry, I'm gonna erase this. So the value function is saying if you have a bunch of trajectories, like what is the average? Some good, some bad. So there's whether your value function is an ideal approximation of the average, even if it's an ideal approximation, it's still approximating the average. And so you're saying, okay, this is the average, and I'm trying to see how much better is this thing than this thing. How much worse is this thing than this thing, right? And so, yeah, even if it's an ideal thing, it's still there. Okay, so the main point of PPO, or proximal policy optimization, is that you just take the essence of this thing, which is saying don't let the policy move too much, and you do it through clipping. So that's it.
By the advantage function inside the min, because it looks like you're multiplying the advantage with 4. So I don't see why it has to be inside of the min function.
Yeah, I think it can be outside. I think it can be outside. Yeah, you can just move this outside. Because it's a scalar, shouldn't matter. But yeah, I guess this is the important bit here, which is saying you take the ratio of pi theta and pi theta I and don't let it move too much. And essentially you start from you can take multiple gradient steps on this objective. It's still an important sampled objective. You can still take multiple gradient steps on it. So you start at some theta equal to theta I, you take multiple steps until basically this thing stops giving you any gradient. Basically it's clipped. And then you switch out theta to theta I and repeat. Same thing as TRPO. But there's no inversion, there's no conjugate gradient, there's no backtracking line search. You just use Adam and like standard gradient descent. right? You just clip the objective. And so all you're doing is restricting the amount that the policy moves. And so you can take multiple steps with mini batch gradient descent. You're not doing any second order or even quasi second order stuff. And it's simple, stable, you can use big networks. All you're doing is clipping.
Do we arbitrarily set epsilon in this case?
Yeah, it's often like 0.2 or something, or like 0.02 or something.
I'm not sure what the combination of min and clip is gonna do here, because it looks like if, you know, the ratio phi theta or phi theta I goes below 1 minus epsilon, the second part would be clipped to 1 minus epsilon, but the first part would go below it. And the min would then return whatever is the least, so the clipping makes no difference.
Clipping makes no difference.
At least on the lower side. On the higher side, it would make,
Yeah, I guess you have.
if I was curious whether there's a reason why the advantage function has to be modified.
Just like or leaky to-
No, it's definitely not just the clip. I copy pasted that from the paper.
I mean, it makes sense, like if it's below the threshold already, I don't want to increase it, but then if it's beyond that, you want to do it.
If it's below, I mean, I guess it's kind of like, I guess what he's saying is that why have the 1 minus epsilon then, right? It's always going to be, or like why have the 1 plus epsilon? So it's always going to be removed by the min. And that's a good question. Your advantage can be negative. Yeah, so then perhaps I guess it has to be that the advantage is multiplied and it can be negative, and so you're taking the min of the thing weighted by the advantage. In which case your logic won't hold. Right? If the advantage is outside, then it's different. But if your advantage is inside, then you're taking the min weighted by the advantage, which can be negative. Yeah, that's a good point. Sweet. Okay, so you can apply this to lots of different robotics problems. Usually it's still too inefficient to run in the real world. Like you don't usually run PPO in the real world, but you can do this stuff in sim. And you can transfer it to the real world and it transfers pretty well. So if you want to do any robot learning or anything in sim, PPO is really nice and stable and works well. You can apply it to things like Minecraft, or this is StarCraft. But you can apply it to Minecraft. And an interesting question is, should we just apply PPO for everything? And so there's a bunch of nice empirical work on PPO versus TRPO versus other algorithms, and they find that small implementation details often matter a lot. So like how you're normalizing your advantages or how you're clipping things or batch norms, like things like that make a big difference. So yeah, this is a good paper. I'd recommend looking at it. So overall, the pros and cons of policy gradient is that it's simple, easy to implement. It often works really well. It often works better than any of the other methods asymptotically. So if you ever want to max out performance, use PPO. Don't use SAC or any of the other algorithms. They tend to do worse. And they don't require a lot of modeling on your environment. So you can like use it black box. So you can apply it to like chip design or graphic, character control or whatever else. But the cons is that it's still pretty sample inefficient because you have to keep changing your policy out fairly often. You're not able to use lots of prior data, just little bits of prior data. And you still require pretty large batch sizes to make this work. And so it's still inefficient. It's hard to debug when it doesn't work. So some kind of open problems that I think are fun to work on here are some of these. I'll just rush over them real quick, but please refer to my slides for other things. Like there's like interesting theoretical questions on the convergence of policy gradient. So like they've shown that it converges to a global optimum in its LQR or LQG, which means your dynamics are linear and your cost is quadratic. But when you go to any nonlinear setting, the guarantees don't hold. And also often the practical algorithms deviate from the theory. So if you look at the gradient estimate, is often pretty far from what it should be ideally, but it still works well. And so there's like open questions on why it works well. There's like questions about scaling. So how do you like do this asynchronously over like thousands of GPUs and thousands of simulator instances? So there's like interesting systems questions there. Better methods for variance reduction. So we've talked about variance reduction being done with baselines, which are state dependent. Folks have thought about how to do this with baselines that are action dependent or different types of estimators. So variance reduction is still open question. It still doesn't work that well from images. Like it still can be unstable and a bit high variance. And so people have been studying things like how do you do this teacher-student type learning model where you learn something from low dimensional observations and distill it into high dimensional image observations. And so that's, but there's like no guarantees for that. And so that's still an open question. How to like appropriately learn from images and in partially observed settings. Going from off policy data. So if you had some prior data, like someone gave you expert demonstrations, how to use them in policy gradient, still an open question. So we talked a little bit about how to do off policy gradient, but it's not super clear how to do it from prior data and do it efficiently and incorporate prior data effectively into PPO. Multi-agent policy gradient is still interesting and open, and I think there's multi-agent PPO and DDPG and a few things, but there's still like lots of space to study convergence, to study better algorithms that leverage, like for instance, there's local structure and lots of multi-agent problems. Like you don't have to worry about all agents. How do you incorporate that into multi-agent policy gradient? So it's still pretty open, and specifically in these three regimes. And then lastly is like, it's not really being used to train robots in the real world. It's being used to train things in simulation and transfer to the real world. How can we make it efficient enough to train in the real world is still pretty open. And so far, I'd recommend using PPO for simulation training and transferring, not training robots with PPO in the real world. So this is lots of stuff from NVIDIA and others where they like train things in simulation, and then you can transfer it to like go on a hike in the bottom that's in ETH and or like do manipulation on the right. So it works really well, but I think it's like doesn't get better when you deploy it, which is kind of the point of RL. So it's still an open question how to do that. Yeah.
It doesn't get better when you deploy it because the reward isn't.
Because you're just not doing RL on deployment. You're just running your policy.
Right.
And why are you not, is the question, why are you not? Because it's too inefficient. You're running policy gradient, which needs like 1 million samples. And so you're not like running PPO in the real world. You're just deploying your policy. And so some perspective here is that policy gradient, it's a pretty solid set of techniques. They give us a reasonable solution to the RL problem by just doing gradient descent on the objective. We talked about vanilla policy gradient, or just the first thing we talked about is policy gradient, natural policy gradient, TRPO, PPO. Each of them have their own pros and cons. Definitely don't use vanilla policy gradient for anything. PPO is better, but it's great for solving black box optimization problems, but it can be slow and inefficient, and there's lots of open problems. So yeah, I think we should kind of end there, but yeah, that's policy gains, and we will do actor critic next time. Cool. Thanks, guys.